All right, thank you very much for the introduction and the invitation, and thank you all for coming here to listen to my talk. It's a great pleasure to be here. So I'm going to give a survey talk on some theoretical and computational aspects of the stable homotopy groups of spheres, and I'll also talk about the Kervaire invariant problem. So let me start with the background story. So Poincaré proposed the famous conjecture, or proposed the famous question in 1904, that if M is a closed manifold, closed means compact, no boundary, it is of dimension 3, and is simply connected. And the question is M homeomorphic to the 3 sphere? So as we all know, in early 2000s, this is answered positively by Pellerman using geometric analytical methods. So this condition being simply connected, like path connected and pi being 0, if you think about it, for a 3-dimensional closed manifold, using things like Poincaré duality, it is equivalent to the condition that this manifold is homotopy equivalent to the 3 sphere. So in other words, in this case, so M being a 3-dimensional closed manifold, if it's homotopy equivalent to the 3 sphere, then it is actually homeomorphic to the 3 sphere. So being homotopy equivalent is a weaker equivalence relation, and being homeomorphic is a stronger equivalence relation. So in this case, the weaker one actually implies the stronger one. That's one way to think about the statement of Pellerman's theorem. So of course, we don't have to ask this question just in dimension 3. We could ask this question in all dimensions. If you take a closed n-dimensional manifold that is homotopy equivalent to the n-sphere, is M homeomorphic to the n-sphere? So in dimension 1 and 2, the answer is yes. So it turns out the answer is yes for all dimensions. So the case n equals 4 is proved by Friedman in the 80s, and in higher dimensions is proved by Smeyer, Newman Connells in the 60s. So the version Smeyer proof needs to require this manifold to have a smooth structure to start with. So in summary, in all dimensions, being homotopy equivalent to the n-sphere, this weaker equivalence relation actually implies a stronger one being homeomorphic to the n-sphere. So we can move on to the smooth category. Then there are more equivalence relations, an even stronger one. So Sn here is a standard sphere sitting inside of Rn plus 1. It has a standard smooth structure. Then then a smooth manifold have another even stronger equivalence relation, namely being diffeomorphic to the standard n-sphere. So we could ask this question, sometimes known as the smooth Poincaré conjecture, namely, if we take a closed smooth n-dimensional manifold that is homeomorphic to Sn, namely the underlying topological space is the n-dimensional sphere, is M diffeomorphic to Sn. So in other words, does the topological manifold Sn have exotic smooth structures? The ones are different from the standard one. So again, in dimension 1 and 2, the answer is always yes. The n equals 3 case is also yes. This is actually known a long time ago due to Moyes in the 50s. So in fact, every 3-dimensional manifold has admit a smooth structure and a unique one. So in particular, the 3 sphere has a unique smooth structure, and therefore it's always diffeomorphic to the standard one. So n equals to 4 case is, of course, the well-known open conjecture, the smooth Poincaré conjecture in dimension 4. And in higher dimensions, so it turns out in dimension 5 and 6, the answer is yes. This is known by Kervaire Milner that the 5 sphere and 6 sphere has a unique smooth structure. And as we know, in dimension 7, Milner discovered an exotic smooth structure on the 7th sphere. So it is homeomorphic to the 7th sphere, but not diffeomorphic to the standard 7th sphere. So in fact, Kervaire Milner discovered that the phenomena of exotic sphere phenomena happens very generally in higher dimensions. So having that in mind, we could ask 2 further questions. So namely, for which dimensions there is still a unique smooth structure on the n-sphere? Or we could ask, if we fix a dimension n, how many smooth structures are there on this given dimension? Okay, so the second question was answered by Kervaire Milner in the following sense. So let me recall this very quickly. So we always assume n is at least 5. So take the set of smooth structures on the n-sphere, denoted by theta n. It has a monoidal structure. If we take the connected sum of 2 spheres, we get back a sphere. So by Smear's theorem, this is equivalent to the H cobordism classes of homotopy n-spheres. So homotopy n spheres are the spheres that are homotopy equivalent to the n sphere. Cobordism means a one higher dimensional manifold whose boundary are two spheres. So this introduces the equivalence relation. H here stands for homotopy, further requires that the inclusion of the two boundaries are homotopy equivalence. So wanting to understand counting the number of smooth structures if the answer were finite is the same thing as knowing the order of this group. So it turns out there is a subgroup which is better understood. This is denoted by theta and BP. These are the homotopy spheres that bound a parallelizable manifold, like the tangent bundle is trivial. And the connection between the subgroup and this big group theta n is the following. So first of all, this subgroup is always cyclic, and the order of this group is almost completely determined up to a factor of 2. So more precisely, when n is even, this is always a trivial group. When n is congruent to 1 mod 4, this group is either order 1 or order 2. This ambiguity, this undetermined factor of 2, is later known as the Kervaire invariant, which I will get to in a minute. And when n is congruent to minus 1 mod 4, for the purpose of this talk, let me just say this is like a big number and increases very fast. So this has something to do with the balloon numbers. So for example, when n equals to 7, this number is like 28. When this number is like 15, this number goes up like 16,000 and beyond. Okay, so knowing the order of this subgroup, how do we connect to the big group? Well, there is a short exact sequence. So when n does not congruent to 2 mod 4, okay, here's the subgroup, this is the big group, and their difference is something called pi n mod j. So pi n here is n's stable homotopy groups of series, which I will define later on in the talk. J here is the J homomorphism. So there is a map from the pi n of the infinite dimensional special orthogonal group landing to the n's stable homotopy groups of spheres. It turns out the image is a splitting direct summand, which is the well understood part of the n's stable homotopy groups of spheres. And this co-kernel of J is the more complicated part. So in summary, Kervaire and Milner reduces the question of counting numbers of n-dimensional smooth structures on n spheres into a problem in algebraic topology, namely computing the co-kernel of J. So when n does congruent to 2 mod 4, the story is slightly more complicated. There's a longer exact sequence. The first 3 terms are still the same as the other case, but there are 2 more terms. So there is a group homomorphism phi n to z mod 2, and there is a further theta n minus 1 BP. So this map, this group homomorphism is known as Kervaire invariant. So if you think about it, any group homomorphism landing to z mod 2, there's only 2 possibilities. Either it is a surjective map, or this map maps everything to 0. So in either case, we can fully determine this theta n minus 1 BP case, which is ambiguity of the factor of 2 in the previous slides. So combining all dimensions, the order of theta n can be reduced to 2 problems. One is computing co-kernel of J. One is asking when this map is 0 or non-zero. So this is known as the Kervaire invariant problem, namely in which dimensions this group homomorphism is non-zero. So I'm going to take a small digression and talk about the Kervaire invariant problem, which has another geometric meaning. So the Kervaire invariant is defined for frame manifolds of dimension 4k plus 2. So frame here means if you have a manifold and can immerse or embed into higher dimensional Euclidean space and have a normal bundle, I can further embed into even higher dimensional Euclidean space to have a stable normal bundle. So the framing means I want the trivialization of the stable normal bundle. So in one sentence, the Kervaire invariant is defined as the following way. It is the Arf invariant of the quadratic refinement of the intersection pairing with z mod 2 coefficients. So let me unpack this definition a little bit. So if you take z mod 2 coefficient, we know that the cohomology gives us our perfect pairing, as known as the intersection pairing. And due to the stable framing, it turns out it corresponds to a quadratic form. This is a non-degenerate quadratic form defined on this vector space over z mod 2, and that's the relation satisfied with respect to this intersection pairing. So the alpha invariant is some invariant which is completely algebraic. It classifies isomorphic classes of non-singular quadratic forms over the field of 2 elements. So one way of having this definition is the following. So it is defined over this vector space over Z-mod 2, so we can plug in all the possible inputs and consider what the outputs are. So since it's non-singular, the number of outputs is either 0 or 1, there will be a difference of values. And the majority of the values is defined as alpha invariant. So this alpha invariant taking values in Z-mod 2 together with the dimension of this vector space gives a classification of isomorphic classes of non-singular quadratic forms over Z-mod 2. So that's like a definition which is a little bit involved for the Kervaire invariant. So why do we care about the Kervaire invariant? So other than the Kervaire-Milnor story, there are some other reasons. So Pontryagin tells us if we consider free manifolds of dimension n, and then we mod out this framed cobordism equivalence relation, this is the same as the nth stable homotopy groups of spheres. So this J part coming from SO corresponds to chamber of framing. So the Kervaire invariant in this sense can actually be defined as a group homomorphism. It doesn't change under cobordism from pi n mod J to Z mod 2. So the importance is the following. So if we work with free manifolds, we can consider whether or not we can use surgery to convert this into a homotopy sphere. So it turns out the lower dimensional homology are always easier to bypass, and the middle dimensional homology is the only part which is hard. And this obstruction turns out to be quadratic and is completely determined by the Kervaire invariant. So this is the only obstruction class that determines whether a stable framed manifold can be converted into homotopy sphere. If the Kervaire invariant is 0, then it can be converted using theory to a homotopy sphere. And if it is 1, then you cannot. Okay? So this is another reason why the Kervaire invariant is interesting. There's another reason. Let me mention that in a second. So the Kervaire invariant problem is asking in which dimensions there exists a manifold that has Kervaire invariant 1. So as I mentioned earlier, this is a group homomorphism. So that means if there is one manifold of Kervaire invariant 1 in a certain dimension, then exactly 50%, half of the manifold after framed cobordism have Kervaire invariant 1, and the other half have Kervaire invariant 0. The alternative would be for all manifolds in a certain dimension, they all have Kervaire invariant 0. So in low dimensions, people have found certain framings on these three manifolds in dimension 2, 6, and 14. They all have Kervaire invariant 1. And Kervaire himself proved in the 60s that when n equals dimension 10 and 18, the Kervaire invariant is always 0 for all smooth manifolds. So one interesting thing here is that when Kervaire first defined Kervaire invariant, it was defined for some more general types of manifold. In particular, it can be extended to topological PR manifolds. So Kervaire discovered a PR manifold which have Kervaire invariant 1 in dimension 10. And at the same time, Kervaire proved that for all smooth manifold in dimension 10, they all have Kervaire invariant 0. So that's the first time in history mathematicians discovered a manifold, a topological manifold, which does not emit any smooth structure. Of course, now we know this phenomenon could happen in dimension as low as 4. But that's the first time we learned this could happen. So that would be another reason why the Kervaire invariant is very interesting. So regarding the Kervaire invariant problem, the next breakthrough is by Bill Browder, and also in the late 60s. So Browder proved that there exists a manifold with Kervaire invariant 1 in dimension n, if and only if two conditions need to be satisfied. First of all, n has to be of the form 2 less than a power of 2. Secondly, there is a statement in stable homotopy theory, a particular element in a spiral sequence called Adams spiral sequence converging to the stable homotopy groups of spheres has to survive, has to correspond to a non-zero permanent cycle in the homotopy groups of spheres, and therefore the corresponding resulting frame manifolds will have Kervaire invariant 1. So in particular, this implies that for the dimensions which are not of the form 2 less than power 2, all manifolds in that dimension will have to have Kervaire invariant 0. So that rules out most of the dimensions. So a more recent result due to Hill-Hawkins-Rabinow announced in 2009 and published in 2016 is that the Kervaire invariant 1 problem has a positive answer only in dimension 2, 6, 14, 60, 62, and possibly 126. So their theorem ruled out dimensions which are at least 254. So the later ones, there's no manifold of covariant 1. So the dimension 30 case was known a long time ago. This is due to Mahawar-Tangara in the 60s. And later on, there's an explicit manifold constructed by John Jones in the 70s. In dimension 62, there's again a homotopy theoretic argument, basically proving the second part of Broder's theorem by Barrett-Jones-Mahawar in the 80s. And as of today, we still do not know any explicit manifold, even though we know that 50% of the manifold in that dimension has covariant 1. It's just we couldn't find one. So basically, for any manifold we can construct and compute the covariant variant, it turns out to all be 0. So more recently, together with Wien and Li and Gordon Wang, we proved that there is a manifold with covariant variant 1 in dimension 126. And again, this is a homotopy theoretic argument. So I will mention some of the ingredients in the proof in the later part of this talk. Yeah. What? Yes. There are 6 dimensions. Yes. Sphere.
What does it mean?
Oh, it could be a sphere. Yeah, it could also be other things, right? It's up to frame cobordism. It can be taken as a sphere. It depends on which smooth structure, like which framing you have. It depends on the framing. So for different framings, you could have either 0 or 1. This could happen in dimension like 2. Like if you take the towers, right? The Euro framing gives you covariant variant 0. But if you take like the circle with this tangent like Lie group structure and the cross with itself, this gives you covariant variant 1. Yeah. So it depends on the framing. Yes. All right. So let's get back to the smooth structure on sphere story. So another question we asked earlier on is that in which dimensions there could still have a unique smooth structure. So a necessary condition would be the subgroup has to have order 1 to start with, right? We are looking at the big group. Okay, so recall that when n is 4k minus 1, this is a Ballooning number story. So this is never unique since this number is like large. And when n is 4k plus 1, it depends on the covariant variant problem. Let's recall this longer exact sequence that this subgroup is 0 if and only if this is a non-zero map. Namely, there is a manifold of covariant variant 1 in one-dimensional higher. And we just learned there's only a finite list of sequences, right? List of dimensions. So combining 4k minus 1 and 4k plus 1, that's all dimensions. So the candidates that this subgroup is 0 are the dimensions 3 less than power 2, namely that could have a unique smooth structure, namely the following list of sequences, list of dimensions. So these are the candidates. So for dimension 5, this is known to Kervaire Milner. For dimensions 13 and 29, this is known to Peter May in his thesis. We know that it's not unique. Actually, we know there are exactly 3 smooth structures on these 2 spheres. So this is known in the 60s. So the dimension 125 case, we still do not know. We have a good upper bound, but we still do not know how many smooth structures on S125. But we do know it is not unique. So one way to do this is to use something called TMF, topological module forms. This is a generalized cohomology theory. Has something to do with elliptic curves, and its first image can see some of the non-zero maps between spheres. That's basically the idea. So we know there are at least 2 exotic smooth structures. And for the final case 61, this is a theorem proved by Gordon Wang and myself in 2017. So we did a computation in stable homotopy theory. We proved that pi 61 is 0, and therefore the 61 sphere has a unique smooth structure. So together with previous results, so that gives the full list that only all-dimensional spheres with a unique smooth structure are just 1, 3, 5, and 61. So this turns out to be the last case among all dimensions. So you may ask, okay, so that's the story for all dimensions. What happens for even dimensions? So first of all, the subgroup always have order 1, so we don't have anything for free. Okay, but based on the computational knowledge we have right now, we make a conjecture. So we don't know what happens in dimension 4, but for dimension at least 6, So only even dimensional spheres with a unique smooth structure are just S6, S12, and S56. So these three cases are known. Okay, the first two are known to Kervaire-Milner. This dimension is known to Dan Isaacson using some Homotopy computations I will get to later. So the conjecture is more about there's no more on this list. So regarding the no more, the progresses are Barnes, Hill, Hopkins, Smallhofer, Quigley. Recently, they confirmed among all the even dimensions, over 50%, there are exotic exotic spheres. And there's some ongoing progress, me with Barnes and others trying to establish this conjecture towards 100%. So the idea is that it uses something called chromatic homotopy theory, which studies periodic phenomena in homotopy theory. So basically, if we can discover a sequence of dimensions, like there's a periodicity, right? There are exotic spheres, there are non-zero elements in the co-kernel of J that should provide exotic spheres in these dimensions, and it covers infinitely many dimensions. If we can construct enough periodic families and covers all the even dimensions, that should be able to resolve this conjecture. But it's still, incomplete. All right. So next, I'm going to talk about review something about the computation of homotopy groups of spheres. So this is the kind of object where in mathematics they are very easy to define. It's just the base continuous map from a sphere to another one modeled out by homotopy, but very hard to compute, it turns out. So there are a few things we know. For connectivity, we know these dimensions, this group is always 0, and we know the copies of these in all of these. So in fact, we know these are always finitely generated abelian group. And in particular, we know all of these. So for the rest of the dimensions, they're all just finite abelian groups. So here's the table for some low dimensional results. So there are two gradings. So I'm putting these things into columns. So a dot here means 0. Infinity means a copy of z. And 2 means sigma 2. 2 squared means sigma 2. Direct sum is sigma 2, and so forth. So this table looks a little bit random, but if you look at it, there are some patterns still, right? For example, this row and this row, they are almost identical. That just corresponds to the fact of the first hop vibration. S1 has trivial higher dimensional homotopy groups, and therefore S2 and S3 have almost the same groups. And you also, another less subtle phenomena is that if you look at the diagonal and you look to the right, you see that each row eventually stabilizes, becomes the same group. But you have to start around the diagonal. So this is actually not an accident. This is a theorem due to Friedensel in the early 30s, proving that this group only depends on the difference of these two dimensions, providing if k is large enough. So this group is referred as nth stable group, the stable or the nth stem, and I will just denote it by pi n. So that's the part that plays a role in the early Kervaire-Milner story. So what do we know about these groups, right? Sayre told us there are always finite abelian groups. If n is greater than 0, then therefore we can compute one prime at a time. Then just use the direct sum to get them together. But if we put all n's together, it has a richer structure. There's a composition, right? So this number is the difference of dimensions of the spheres. You can take a composite, then we get to a ring structure like this. So this is a commutative ring in the graded sense. There's also higher products, especially the total brackets. So if you have two elements, the consecutive composition is 0, is homotopy to 0, so is the other pair, then we can form a higher product called the total bracket. So when we do these computations, we would like to understand these structures as much as possible. All right, so here's a table for the stable groups. So there's only a single grading, but I'm putting them down in like 8 periodic pattern, as you can see. So this table only goes up to 55. Now we know around like 90 something now. Okay. So you see that there are a bunch of dots. That's just 0, and there are a few groups that has underline. So that's the image of, that's the J part. That's the image of J part. Whenever there's an underline, there's the image of J part. So due to the Bott periodicity, the homotopy groups of SO has this 8 periodic phenomena, and that's image in the homotopy groups of spheres. That's well understood. You also see a bunch of random like prime numbers, like 19, 23 showing up everywhere, right? So it's known that all of these kind of like finite abelian groups will show up in this table somewhere eventually. So another way to organize the data is the following. So this is just the prime 2 computation. Okay. So I don't know if you can see this. Okay, now it is better. So you see a bunch of like dots and lines. So pi 0 is z. I'm looking at the prime 2 information. This is just the two-adic integers, but I'm giving a filtration. So the vertical one is a certain filtration, and this direction is just the stem. So that's the 0 stem, that's 1 stem, 2 stem. So pi 1 is sigma 2, pi 2 is sigma 2, pi 3 there are 3 dots. So instead of 3 copies of sigma 2, it's actually sigma 8. So that's certain groups extension. 4 and 5 are both 0, 6 is sigma 2, this is sigma 16, sigma 2 plus sigma 2, and so forth. Okay, so that's one way to organize the data. But you see that, so this is, of course, the E-infinity page of a certain spectral sequence, which I'll get to in a second. But there are some interesting phenomena you can see globally that there's a vanishing line, and around the vanishing line, there's a pattern. So that's the J pattern, right? That's roughly speaking 8-periodic. Okay, that's also known as the K1 local sphere, or the height 1 part of the chromatic layer of the stable homotopy spheres. So that's a well understood part. But then you see a big gap in here. And by the way, the theorem about 61 is just to showing that in the 61 column, there's no dots left, and therefore pi 61 is 0. So this turns out to be a something called the E-infinity page of the atom spectral sequence. So this layer corresponds to homotopy groups of Lie groups, but along this vanishing region along here, that's the part seen by things like topological module forms. So these are high 2. So roughly speaking, every dot in this picture, an element in the stable homotopy groups of spheres, it should fit into one periodic family. So here, things are roughly just 8 periodic. But in the high 2 part, in this part, things could be something like 192 periodic, because TMF its homotopy groups is 192 periodic. And for later layers, there should be even higher periodicities. So this is a picture only up to 90. If we were to have a picture, say, up to 1,000 or 10,000, we should expect to see a few more layers. So the whole thing will look like a rainbow, and there are a few gaps. And because the periodicity has a certain dimension and certain filtration, so things will lie on different slopes. So that's the expected picture. Okay, and the next picture is the Adams E2 page. As you can see, there's no gaps. There's just a lot of dots in between. So this is actually something we can compute. The E2 page can be computed using even a computer program using homological algebra. So the hard part of the story is to determine these differentials. Okay. All right. So next, I'd like to talk about, before I talk about these computations, so let me give you a warning. So there's something called Mahoward uncertainty principles. Okay, so these are principles, they're not theorems. It's just like a belief or something. Okay, so the first Mahoward uncertainty principle states that any spectral sequence converged to the homotopy groups of spheres with an E2 page that can be named using homological algebra, like the atoms is one such example, will be infinitely far from the actual answer. In other words, there will be infinitely many of differentials need to be computed for such a spectral sequence. So this problem of computing stable stems is not an algebra problem. It's not a homological algebra problem in nature. We need actual topological inputs or other methods, other theories to compute these differentials in the atom spectral sequence. So based on my experience with Mahoward, I proposed a second principle. So when I started as a grad student, I asked Malcolm Howard, there's so many methods computing the stable homotopy groups of spheres, which one is the best? I was being lazy, I just want to learn the best method. But Mahoward's response was, well, there's no best method. You really have to combine all existing known methods in order to push forward computation a little bit further. So this is actually, in fact, true of what happens in history. So over the years, people have tried to push this computation using known methods, but then they got stuck at a certain dimension. We still know a lot of partial information later on, but you get stuck on some differentials at a certain dimension. Then another new method was introduced, and people keep going, and this happens many cycles in history. So based on that spirit, I propose a second uncertainty principle, namely, any single method that computes such differentials will leave infinitely many differentials undecided. All right, having that said, so let me review the history of who computed what. So Serre, using the Serre spare sequence by studying the fibrations among Allenberg-MacLane spaces and computing up to 8 stem using the unstable method. So in particular, you know the stable range. Then Toda introduced the EHP sequence and managed to compute up to 19 stem. So these computations are all integral and all both like bi-grid and stable. But in particular, you can read out the stable information. So if you only care about the stable information, the Adam spare sequence is some kind of stable version of the Serre spare sequence. And Peter May, in his thesis, he constructed another spare sequence called the May spare sequence that computes the Adams E2 page. So that's a trigrided spare sequence converging to the bigrid Adams E2 page. And then using Toda's computation, you know the answer. You can deduce the differential backwards and use a multiplicative structure of the Adams spare sequence, and we're able to determine this up to 28 step. So, but then May got stuck around dimension 30. That's due to the Kervaire invariant problem in dimension 30. So that problem was came by work of Barrett, Mahavar, Tangara. They gave a deeper study of the Adams spare sequence, and they managed to push up the computation to dimension 45. So some of the techniques involved are, so there are massive products in the algebraic Adams EM page. There are also Toda brackets in topology. There are certain connections by Moss theorem, but there are some very technical conditions involved. Mahavar always introduced a trick that you can translate differentials and certain extension problems using certain finite CW complexes designed to study certain differentials in these spectral sequence. Then pretty much people get stuck for quite a while. So during this time, there's also work by Kochman and Mahavar using completely different story. But later on, they're not very compatible with the Adam story, and people found errors that are that people do not understand how to fix them. So I would just skip that part. So more recently, Isaacson first studied the motivic version of the Adam spare sequence over the complex numbers and gave rigorous arguments up to 59 stem. So I will mention how the ideas of his method. But then again, he got very stuck at the stem 60 and 61. So when I introduced another method, this is rather classical. We call this the RP infinity method. So this method is not designed to do large range computations, but it's more designed to target a specific differential. So there are 3 differentials that are very hard to prove, and people don't know how to do this from the motivic or other classical perspective. So we use the RP infinity method to prove them. So one differential in particular took us 40 pages to write down the whole argument. But the good thing is there are later stories later on that, in particular, in the next motivic Kervaire method, we have a one-line proof for this 40-page differential. So this motivic method, Kervaire method, is also very different from the Isaacson motivic method. I will explain what that means. But using this motivic Kervaire method together with Isaacson, we can compute up to 90 stem with very few exceptions. There are some computer-based computations, but we're not writing them down. But the ad hoc part also took us like more than 100 pages, but we give a lot of differential computations up to 90 stem. So some of the few exceptions are done by Birkeland, Isaacson, and myself. We have another theory which is more parallel to the motivic story. This is called a synthetic homotopy theory. So we can manage to prove a few differentials. So now we know basically everything up to dimension 90. But apparently that was not enough for the Kervaire invariant problem in dimension 126. Things get extremely more complicated later on. So then together with Lin and Wang, so we now have some even newer method. So we can give a complete computation up to dimension 93, but we have a lot of partial computations beyond even dimension 20. And in particular, with whatever the partial information we have, and plus some other methods, we can resolve positively for the last Kervaire invariant problem in dimension 126. So we'll get to that later. Okay, I still have like 25 minutes or? Okay, great. All right, so this is roughly speaking the range up to dimension 90. So that's Serre, that's Toda, May, Barrett, Mahavar, Tangara. This very, 2 columns is just the 61 sphere story, and that's the motivic thing. As you can see, there are a lot of the complexity becomes much more complicated. So basically, the way the differential works is that if you have a dot in a certain column, then the differential exports goes to the left by 1, goes up by any length starting from 2. So basically, if you want to determine the fate of the dot in one column, all the dots on the column left to it could be the potential target. So there are a lot of possibilities to rule out. All right. So I'd like to first mention of some of the recent motivic methods. So motivic homotopy theory was introduced by Morel and Wolski, and is designed to use abstract homotopy theory to study problems in number theory and algebraic geometry, and was very successful in Wolski's resolution of Blockato and Billington-Littenschwamm, etc. So I would just focus on the idea that's related to this project. So you can think this motivic category is a mixture of smooth schemes over a field together with this spectra in algebraic topology, namely the representing objects of generalized cohomology theory. So there is such a category classically, namely the stable homotopy category. This is like a triangulated category, if you like, or stable infinity category. So objects in here are both a generalization of the suspension spectrum of a topological space or the representing objects of a generalized cohomology theory. And motivically, we mix in more things from algebraic geometry, and for any base field K, there is a corresponding stable infinity category called the motivic stable homotopy category. So I'm denoting it by SHK. So in the classical category, there is a single gridded sphere, and if you invert that, we get a stable category. And in the motivic setting, there are two types of spheres. The simplicial one comes from topology, and this multiplicative group comes from algebraic geometry, and that's the corresponding grading we have, and we smash them together, we get P1. So if we invert both types of spheres, we have the stable category. So as a result, in the motivic setting, we have bi-graded motivic homotopy groups, motivic homology groups, and etc. And of course, we can also define the motivic bi-graded homotopy groups of spheres. So here's a quick summary of what we know for the motivic stable homotopy groups of spheres. It's defined for any base field K. So Morel proves that for any base field K, pi n comma n of the sphere spectrum is just the n-dimensional Milnor-Rake K groups. And recently, Roddick's, Spitzberg, and Osbeer proved that n plus 1 comma n and n plus 2 comma n of the sphere spectrum can be expressed in terms of a Schroeder sequence of motivic cohomology Hermitian Milnor K groups of the base field K. So in this sense, you can think that these motivic bi-graded homotopy groups of spheres can be think as the generalization of certain arithmetic invariants of the base field K. And regarding specific fields, so there are some computations done using various Adams type of sphere sequences for C, R, and some finite fields, and that's the known range. And recently, together with Bachmann and Birkeland, we have some further description of some reconstruction of the whole category, in particular for some base field, such as the field that contains all the p to the nth roots of unity. We can have an expression that the homotopy groups of spheres for the completed sphere can be expressed in terms of the things over an algebraic closed field. So there has been even more fields we can actually talk about the answer, but the formula is not as nice as this one. So in particular, we even construct something has a certain universal property, and we joke about talking about this could be a field with one element or something, but we can describe its homotopy groups, and it maps to the motivic bi-graded homotopy group spheres for any base field K. But anyways, so for the story that I mentioned earlier, the more relevant story is over C, because over C there is a functor, a Beatty realization functor. So if you take an algebraic variety over C, you take the C points, you get back to a topological space, then this construction can be extended to the whole stable infinity categories. And there is also something special about C, that there is a map between the completed sphere, which is called tau. It lives in dimension 0, -1. So Wolski's theorem, this is essentially Blockato, that the motivic homology of a point, the pi star star of the motivic Einberger-MacLane spectrum, is Fp adding tau as a one generator polynomial ring. So this tau map between spheres can be detected by the motivic MAP cohomology or homology. So under the Beatty realization, these bi-graded spheres, we just ignore the second grading and get back to the topological dimension, this motivic Eilenberg-MacLane spectrum gets back to the classical one, and tau in particular is sent to 1. So people have studied the motivic analog of all the classical computational tools. There is the motivic atoms based on HFP. There's also something called the motivic atoms Novikov square sequence based on MU, the complex cobordism spectrum, or in the motivic setting, MGL, the algebraic cobordism spectrum. So people have studied these motivic analog of the computation tools in these motivic categories. So one important thing oversee is that Dagger Isaacson proved that if we work with cellular modules over the completed sphere, so that's essentially the whole category, but cellular ones, and if we invert tau, this gives us back to the classical p-primary stable homotopy category. So this part of the information, if we just invert tau, it's the same as the classical information. So in particular, if we were to able to compute all the motivic homotopy groups of spheres, there's an extra grading, but if we can compute that and we invert tau, they give us the classical stable homotopy groups of spheres. So basically, by studying the motivic atom sphere sequence together with this comparison inverting tau story with the classical atom sphere sequence, so basically, all the tau-free elements will correspond to something classical, but now we have a third grading. And differentials puts on restrictions of when a differential can happen using the third grading, and that allows Isaacson to rule out a few possibilities which cannot be seen in the classical sense. And using this idea, Isaacson gave rigorous computation up to the 59 step, classically and also motivically. All right? So another important observation is that the motivic atoms Novikov is rigid. So what do I mean by that? It means that it is actually a Tau-Bachstein sphere sequence. So we have the classical atoms Novikov, we have the motivic atoms Novikov. Here there's the third grading. It turns out the E2 page is just adding tau as a free polynomial generator. So everything is tau-free here. So inverting tau gives us back the classical information. So that would mean that the motivic one should contain strictly more information. But in fact, it is not true. The atoms contain strictly more information, but the Novikov doesn't. It actually contains the same information. So that's the rigidity part. So if we have a classical atoms Novikov differential, a non-zero one, due to sparseness, so it can only take the form of length an odd length, 2r plus 1. Then it will force a motivic atoms Novikov differential. It's just how the grading works. It still x equals y, but you need to decorate it with tau to some power, and this power is determined by the length of the differential. So in this sense, the classical and the motivic one, they determine information of each other. But now if we look at the co-fiber of tau, we just mod up by tau. This is like a two-cell complex. So Gregory proved that this is actually an E-infinity ring. And this one, its motivic atoms Novikov, it just collapses at E2 page because there's no tau anymore. So there's no non-zero differentials anymore. Everything just survives. And as a result, its bigraded homotopy groups can be completely described as the X group over this Hopf algebroid, mu star mu. So this is a very surprising theorem because classically, just one cell is a sphere. The answer is very complicated. But motivically, a two-cell complex, we can have a up to infinity general description in terms of homological algebra. So what's the understanding? What's the good understanding of this theorem? Well, then we did some kind of like experiments. So the Novikov collapse, but the atoms is still complicated for cover tau, and Isaacson computed up to a large range. And the left-hand side is something purely algebraic, and there's another spiral sequence converging to it. So Wang made a computer program computing the left-hand side, also into a large range. And when we compare the data, so we know they're going to converge to the same thing, right? But it turns out, starting from the E2 page, all the pattern of differentials, they all have the same data. So that shouldn't be a coincidence. It should be a theorem up to infinity. That's a theorem we prove that these two spiral sequences are actually isomorphic. The way we prove this is that we have to prove that there's an equivalence of stable infinity categories, or triangulated categories, if you like. So the left-hand side are cellular modules over this infinity ring S mod tau. The right-hand side is the derived category of a certain abelian category, namely the comodules over this Hopf algebroid. So this category is well understood in algebraic topology. By work of Quillen-Morova, this is the same thing as the Cauchy coherent sheaves over the modular stack of one-dimensional formal groups over F over ZP, the p-adic integers. So this theorem further connects motivic homotopy theory to chromatic homotopy theory. So one way to think about this theorem is the following. So in the middle, modules over here are just the whole motivic category. And if you invert tau, you think tau as a parameter that lives in the homological point, that gives us back the classical category. But now if we also mod out by tau, it gives us this derived category of a certain abelian category, which is like more algebraic in nature. And the fact we prove that the two spiral sequences are isomorphic is precisely to prove that the algebraic spiral sequence is an Adams type spiral sequence in this category. And since the two categories are the same, so the corresponding Adams spiral sequences has to be isomorphic. So, so in other words, you can think that there's a deformation story that the generic fiber is a classical story, and the special fiber is this specific algebraic category that we can, compute spiral sequences of. And in practice, that's how we use this method to compute things up to 90. Namely, so this motivic Adams is an algebraic Novikov is purely algebraic. We can run a computer program, compute this spiral sequence into a large range. So all differentials we obtain are like for free. In particular, for that differential in dimension 61 took us 40 pages. That's just a one-line compute output. Then we just pull back to the motivic Adams. When we take a Beatty realization, we invert tau, we get back to a classical story. So that's roughly speaking how this works. So combining with other, classical ad hoc methods, we were able to compute up to 90 steps using this method. So I should mention that this deformation story, there are other stories over other base field, but the story is more complicated. So we figure out like a T structure, and there is a positive tower, and so the layers are more complicated, but there's still some game we can play. In particular, the heart of that T structure, we call the child T structure, are always this mu star mu comodules, and which allow us to play this game over other base field. But this one is more closely connected to the classical story. So later on, there has been some newer developments called the synthetic homotopy theory. This is introduced by Piotrowski. So it is more like a parallel story. Okay, so this category of synthetic spectrum is also have bigraded spheres. There is a map of degree 0, -1. We call it lambda. There is a corresponding Ehrenberg-McLean spectrum in this category. Its homological point is again this polynomial ring. But the deformation story is a little bit different. Okay, when we invert lambda, we get back to the classical stable homotopy category. But if we mod out by lambda, this just corresponds to the derived category of the comodules over the dual single algebra. Because this story is more based over HFP, as the motivic one is somehow more based over the complex cobordism ring. So you can think that the cellular C motivic story is a categorification of the Adams Novikov spiral sequence, while this theory is more like a categorification of the Adams special sequence. And the connection is that this synthetic one, you can put in any E theory, and there are also work by Gorgi, Eggerson, Cross, and Rika. They form something called filter spectrum, and this construction turns out to be all equivalent, and this is the motivic story. And as a parallel story, the atoms will have the rigidity that the synthetic atoms and the classical atoms, they determine information of each other, but this gives us more room to play with the atom spiral sequence, basically. All right, so finally, I'd like to talk about the more recent ingredients that towards the last case of the Kervaire invariant problem. So there are 3 or 4 major ingredients. The first one is Lin's program. So computing the X group of an Adams type E2 page, like X over a half algebroid, is not a hard problem. People know how to do this. So, but for things like the dual single algebra or other things, it's not commutative. So we now made some generalization of the Grover basis theory for non-commutative algebras, such as Steenwald algebra, and managed to compute this in a more effective way. So, and we are not just doing this for the sphere, we're also doing this for many of spectrum, something such as finite spectrum or KO, TMF, things like that. So in the current version, we involve like 49 spectrum. So Venus program not only computes the additive structure, but also the multiplicative structure in a large range, and also the maps. So we have maps among spectrum, give us the naturality of maps among atom sphere sequences. So Venus program can compute the X among these X groups. So there's also something called the secondary stimuli algebra. This is a theory recently by Giblides, Nassau, and Bowers. So basically, so the stimuli algebra are the primary cohomology operations. If you have a cohomology class that vanishes on a primary operation, and we have a relation of two primary relations, so you can form a threefold total bracket. So these are called secondary operations. And you put all the secondary operations together, you get a secondary analog of the stimuli algebra. Its homology would be the Adams E3 page. So using this theory, we can deduce a lot of D2 differentials, basically all the D2 differentials. So there has been programs made by Dexter Tran and also by Weinan Lin that you can compute effectively of the D2 differentials. Then use the naturality, you can get a lot of other differentials. Weinan's program also propagates differentials and extensions in a smart way. The logic is rather simple. It's just like one-step logic, but it can get you into a huge quantity and play with these differentials. So we actually have a compute output, give a big Excel sheet of the logical chain, like which differential implies another one, like from which spectrum, things like that. So for the problem in dimension 126, it is about a specific element in dimension 126, whether that or not that element survives in the atom sphere sequence. So as I mentioned, elements in dimension 125 are all the potential targets, and there are 105 many of them. So using this big data, so to speak, and the third ingredient, we can get rid of 101 elements out of it. There are 4 elements remaining. Then this HF2 synthetic or filter spectrum technique comes in, so which are motivated from the motivic world. So basically, classically, when we talk about naturality, we have a dr differential. Naturality gives us a dr differential. It doesn't come from a dr differential give us a dr plus 1 or dr plus 2. It doesn't jump filtration. But since we can use things like the synthetic or filter spectrum, any element on any page can be viewed as a bigraded homotopy class. Then therefore, naturality makes more sense as this jump of filtrations. So using this setting, we can form something called the generalized Leibniz rule and generalized Mahorter trick that allows us to further rule out 3 out of the 4 elements, together with the last ingredients, namely the hot arguments near stem 126. So the computer program doesn't know this element survives. It only knows it survives to the E7 page. So we have to do something else. So before Hill-Hopkins-Ramanujan's approach, there is something called the Bayer-Jones-Mahorter's inductive approach, trying to establish all the Kervaire dimensions. They're all positive. So precisely, if one class exists in a certain dimension, it has order 2 and square is 0, then the next case survives and has order 2. Okay? But of course, we now know it has to break down somewhere. So Burkhardt and I give an upgrade of this inductive approach, specifically targeting to the remaining case 126, and we had a result that this element exists, like it's a permanent cycle, if and only if a certain relation has to hold in the synthetic category. So classically, this lambda is this synthetic extra stuff, right? Classically, we know e to theta 5 squared has to be 0, but that just means synthetically it corresponds to lambda torsion. But how torsion that is precisely when this exists. And more precisely, we can form a statement that this H6 squared supports a differential, a non-zero differential of a certain length, if and only if this relation is true in S mod lambda to a certain power. So this method can be used to not only prove theta 6 exists, or the other way around. So the previous Hill-Hopkins-Ramanujan detection method can only be used to prove in third dimensions the Kervaire invariant does not exist, there does not exist a manifold of Kervaire invariant 1. And the previous dimension 3062 method can only be used to prove in certain dimensions there is a manifold of Kervaire invariant 1. But this synthetic method targeting for the specific element can be used to prove both ways. But turns out using all the remaining data and the detailed analysis run dimension 126, we can actually prove that this is 0 and therefore this is a permanent cycle. So there are manifolds of covariant invariant one in dimension 126. Okay, in the last maybe 2 minutes, 5 minutes, let me mention some future direction. So in the Adams spare sequence on the one line, there are elements called Hj. The whole one line is generated by these elements. Adams proved that the first few survives, and the later ones they don't. Okay? The case in dimension j equals 4 was actually first known by Toda, but Adams proved the later ones. So that corresponds to a geometric fact that the tangent bundle over Sn is trivial if and only if the sphere has dimension 1, 3, or 7. The first two are Lie groups. This one comes from the octorions. That's one way to see it. So for the Kervaire problem, it's about this class Hj square in the Adams spare sequence. And again, the story is the first few survives, and later on they don't, and there is a corresponding geometric statement that exists in a free manifold with covariant invariant one. Of course, we still do not know the explicit differentials on later ones. That will be very interesting in homotopy theory perspective. So recently with Birkeland, we proved that the next case, Hj cube, survives. Again, only the first few survives. Later on, they don't. But in this case, we actually know the explicit differentials on these classes. They all support non-zero D4 differentials. So what's remains to be explored is that interpretation in terms of free manifolds. So there's some work by Hans Miller and J.R. Laus that the Adams spare sequence, as we know, is by taking resolution with respect to HFP. But we can also take the resolution with respect to MO, the unoriented cobordism spectrum. So from the homotopy theoretical point of view, it splits as vector suspensions of HFP. So that means the Adams E2 page, if you use resolution of MO versus HFP, they give you the same answer. But now, for any element in the Adams spare sequence, it is in the homotopy group of MO smashed with itself a few times. So that should give us a perspective can be translated into a free manifold with corners. If it's on the one line, that's just with one corner, namely you have an n-dimensional manifold, and the n+1 dimensional manifold's boundary is this n manifold. If it's on the two line, it should give you n, 2n+1, and 1n+2, and so forth, with certain compatible framings this work. So Hans Miller can translate the half invariant problem and the covariant invariant problem using free manifold with corners, and it can, in terms of, in the half case, is the Stiefel-Whitney numbers of the corresponding free manifold. And for the covariant invariant, you can translate that into the products, a sum of products of the Wu numbers. So I think it's possible that we can, this is on the 3 line, to also interpret this into a free manifold with some other characteristic numbers. And that would be great. And okay, so for the next case, Hj to the 4th is 0. That doesn't look good. So what do we do next? But fortunately, there's something called the new doomsday conjecture. It's proposed by Minami. So in X, there are some operations square 0 that behaves like Frobenius. It doubles the total degree. It sends Hj to the next case, Hj squared to the next case, and so forth. So we can form something called the square 0 family by just taking the iteration of this operation. So Minami proposed the new doomsday conjecture, saying that for such a non-zero family, only finitely many of classes will survive. And if this were true, that would be saying that for any square 0 family, that should correspond to the list of dimensions of free manifolds with certain geometric structure that could only exist in certain dimensions. So the height, so the filtration 1 case is equivalent to the half invariant one problem because that's only families. So the filtration 2 case is essentially equivalent to covariant invariant problem, which we now know the full answer. For 3 case, we know the answer to 1 family, but there are still many cases remaining in the form of like massey products and so forth. But hopefully, one would be able to translate some of these square 0 families into free manifolds and tells us there are certain structures only exist in certain dimensions. And based on our computation, we also have a more refined conjecture regarding exactly how they die, that they should kill each other in a certain way, and so forth. All right, thank you for your attention.
Questions or comments?
have no idea, right? So John Jones have this construction of a manifold in dimension 30. I think many people have studied, tried to generalize that to dimension 62 and failed. So yeah, there are some online comments regarding ATIA have this idea of how do you construct the case in dimension 30, 62, and 126 using CP2, HP2, and OP2. But I think people haven't been able to make precise even for the dimension 30 case. So I have no idea. Yeah. It's just a very bizarre fact, right? There, half of them are this is we couldn't find.
Other questions? Maybe I have a question. You mentioned that 61st stable homotopy group is trivial, right?
Yes.
Is it the last place where it is trivial?
I mean, that's in some sense the conjecture, right? It's unknown. But as you can see, the E2 page is very crowded. There's just so many elements, right? The image of J covers a lot of dimensions. Like basically every A dimension covers 5 of them, but they don't really contribute to the exotic smooth structures, right? But anyways, it's hard to imagine. Later, I think for now, as in dimensions, we know up to dimension 20 to 200, there's only one dimension we don't know the precise answer. But there are still a lot of dots there, right? It's just we don't completely understand the pattern of the differentials. So it's very hard to imagine there's another dimension where all of a sudden everything is gone. But I don't have a better reason than that.
Yes, but it's an open question, right?
It's an open question. Yes.
Do you think it is possible to solve it like without computing all the groups?
Right. I mean, the idea was mentioning using chromatic homotopy theory is basically we don't have to know the full answer. All we need to know is like one particular element in that stem survives, right? And chromatic homotopy theory is designed to do this because each time we construct a family, a periodic family, that should cover infinite many dimensions. But it, like the gap is the same, right? If the high 2 story is good, the gap is only 192, so you have something like 20 plus 192, 20 plus 2 times 192. So that covers a lot. But you still need a lot of families in high 2. But if high 2 doesn't do the job, you go to high 3, the periodicity is much larger. You need a lot more families. Then things could be, more complicated. Yeah.
I see. Thank you. Let's thank the speaker.